As of right now, we have finished with the test material. So today I'm going to go over how to go about solving most of these test problems that were given last year, because this is probably going to be somewhat similar to the test this year. I will probably have that test ready on Monday. Probably ask that you turn it in Friday. I'm going to send an email to remind this. If I get it done before Monday, I'll just send it out via email to everyone sooner rather than later. I might put it on Schoology in case you don't check your email, but I'll try to send out as many different ways as I can to make sure everyone's got a copy. Only problem is, like, if you have no internet, obviously that might be a bit of an issue. But so let's go ahead and get started. First thing to note, I am, once again, if it's a take home, I am not including all these tables and tables of data. So what you have to do, one, I haven't given you your tests back, but one thing that you need to do is cite where you got your data. Some people had lost points because they had different data from me and then you didn't cite it, and I might have been able to find it online, but not super happy of having to look. And some of you did cite it, but I still don't like the sources. If you're going to cite it online, things I would suggest would be like scientific things. Your book is always a good source. That's where I'm going to probably get the data from your book. But Wikipedia is acceptable. I would trust Wikipedia a little bit more than maybe Chegg, because a lot of these data points, depending on how you measure them, like small little things, like the KSP will vary by 2 to 5 times greater or less than. Your Ka will depend by a little bit, depending on how it was measured. So if you're doing a acid-base problem with a Ka that reads this and a Ka that reads that, you're going to have like one pH might be like 4.5, the other one might be 4.3, even though you're doing all the right math. And if you're not citing where you got those numbers, I can't be like, oh, well, okay. Well, it all makes sense, as opposed to like, hey, pull those numbers out of thin air. So no matter what site, like, I grab these data points from here. This is a trustworthy source. Wikipedia may not be the best for politics, but it's pretty reasonable when it comes to science, honestly. But your book will have them all listed in one spot, so that's usually a good place. But okay, I just want to start that before I go into this. So what is the Gibbs? So we have this reaction: iron Fe2O3 plus 3 carbon goes to 4 iron and 3 CO2. What is the Gibbs free energy at 650? What is entropy of universe at 150? And what temperature would this be at equilibrium? Now, it would be all nice and good if I could just find our delta G values from and just use those. But because it's not done at 298, I have to use this equation. I have to use delta G equals delta H minus T delta S over 1,000. That 1,000 turns our joules into kilojoules. So I'm going to use, this is the old book, the Brown-LeMay book. This is not the online book, but this is where I'm going to get these numbers. So where am I pulling these numbers? I'm pulling them from this book. So look at that, carbon, graphite, the delta H and delta S of carbon. The delta H is 0. The delta S of carbon graphite is 5.69. CO2, gas. CO2 gas. I'm just writing them down where they're convenient and the margins, because I need a delta H is negative 393.5 and S is 213.6. The tables typically put them in alphabetical order by element name, not element symbol. So iron comes after iodine, not by francium. Okay. Iron solid is 0. Iron solid delta S is 2715. And if anyone wants, I can play the Jeopardy theme. And I gotta find a place for Fe2O3. Fe2O3. Delta H of this guy is, I'm not using Fe3O4. I'm making sure I'm not using FeO. I'm using Fe2O3, which is negative 822.16. And S is 89.96. So I got all these data numbers from the table. Now, question.
I don't think this is on this problem yet, but it's not on this. It's not on this kind of problem. But the E, remember when you have to look at the formula and you have to see which one's the forward one and which one's the reverse, and then have to subtract or whatever to get your E. Is there gonna be one of those on here? Because I'll have a question about that. All right.
Yeah. Number 2 is one just like that.
Okay. All right. I'll ask it when we get to there. Then.
Okay. So I'm gonna calculate what is my delta H. My delta H is products over reactants. So rather than try to write this in, I'm going to say, so our products, 4 times 0, because it's 4 irons plus 3 CO2s times negative 393.5 minus reactants. 3 times 0 plus 2 times negative 822.16.
Reactants come first?
No, products.
Okay, that's what I thought.
So products. So there's our iron and our CO2. There's our carbon graphite and our iron oxide. So it doesn't matter which order you're adding these two together, but it doesn't matter which order you subtract. So it's always final minus initial, because we're looking at a change. Final minus initial. So negative 393.5 times 3 minus a negative 822.16 times 2, because the zeros drop out. So, and this you get a positive 463.82. Now, let's make sense of this. I am converting iron ore with coal back to iron that I can build in a furnace, that I can use to build steel with. Now, does that make sense? How do they make steel? You've ever seen like steel workers? They're using a blast furnace. They're using incredible heats to turn iron ore into steel that we can use to build in construction. They need incredible amounts of heat to do this. That makes this reaction endothermic. This makes this a positive delta H. So hopefully that makes sense. Now look, S. Do it again for S. There's no zeros for S, so we have to do this right. So 3, well, let's do it the same order. 4 times iron, which was 27.15, plus 3 times, let's see, 213.6, minus 3 times 5.69, plus 2 times 89.96 equals. So solving for this, products minus reactants again. Products minus reactants. Now, this should also make sense as we sum this up. 2 times 6. This has a positive 552.41 joules per mole Kelvin. Now, yes, we're going. This is a complicated molecule, but this is very simple, and we're going from 5 solids to 4 solids and 1 gas, and and 3 gases. When we go from solid to gas phase, we increase the randomness. So we see an increase in entropy as we do this. So finally, calculate the delta G at 650. Delta G equals 563.82 minus, what's the temperature? Not in Celsius, but Kelvin. 650 plus 273 is 923 Kelvin times 552.41 divided by 1,000. So delta G is, do all this.
It's a minus, ain't it?
Hopefully.
Oh, okay. I see.
So we get negative 46.05. So yes, we at 650 degrees Celsius, is a temperature that will allow steel to be converted back into iron ore to be converted back into steel. Just erase this so we have more room again. So the first answer, oh crap, undo. The first answer was negative 46.05. Yes, that took a lot of work.
What was the final answer?
That's the answer for A. That's the answer for A. That took a lot of work, I know. But B can use the work we took for A to get there, because entropy of the universe is going to be equal to S minus H over T times 1,000. So entropy of the universe is going to be S minus H over T at times 1,000, because entropy wants to be in joules per mole Kelvin. So using we have our H, we have our S, so we can say our S, 5S universe equals 552.41 minus minus 463.82 times 1,000, all divided by what is the temperature in Kelvin. Well, 150 degrees, add 273, puts it at 423 Kelvin. So solving that by 52.41, that's 463.82 times 1,000 divided by 423.
So those are your delta H and delta S values for S and H?
Yep. There's our delta S. There's our delta H. That's the one we found in for part 1. They're still the same. We're just finding this at a different temperature. So I get our entropy of the universe is negative 544. And I ask, what is the significance of this sign? Well, that means this is a non-spontaneous process at 150 degrees. A negative delta H, and a negative entropy of the universe means this will not happen at that temperature. So 150 is too cold to convert steel, but 650 is plenty hot enough to convert steel. So the final question is, what temperature would this reaction be at equilibrium? So the last thing is, we're setting delta G is equal to 0 and solving this equation. Delta G is equal to 0 and solving this equation. So we get that the final equation is the temperature is equal to delta H times 1,000, 1,000 divided by delta S. So the final reaction, once again, uses all that lovely data we just found for part A. Part A had a lot of work to it, but if you did it right, part A contributes to part B, contributes to part C here. So we're just saying 463.82 times 1,000 divided by 552.41. Please note, this is one of those situations where they both have to be positive or both have to be negative to make any sense. If one is positive and the other is negative, you're not going to be able to, it's either always going to be spontaneous or never going to be spontaneous, because you cannot have a negative temperature. You cannot have a negative temperature. So it's just, if one of these was negative, at what temperature would this reaction be at equilibrium, where delta G is 0? You'd say this is never at equilibrium, or it will never be non-spontaneous. So the temperature at which this is going to be spontaneous, non-spontaneous, 839.6 Kelvin, which if I subtract 273 is going to be 566. So 566 is the minimum temperature you need to make this reaction go. So just a little bit below 650. But that's an example of a delta G, delta H, delta S. Please note, cite where you got your data. Use a reliable source. Your book is a good one. If you got another chemistry book, cite that book. Wikipedia is acceptable. I don't know, some random blog on the internet, maybe not so much. If you find like some like NIST, like some scientific website, maybe. But some of them are like, I don't know. Can I, okay, do I have to? Let's scroll down. Okay. So that was just one, which is 15 points. Okay. 2, answer the following related electrochemical questions. Okay. First, balance this guy. So how are we going to balance this guy? We're going to split this into 2 half reactions and work from there. So half reaction 1, platinum chloride 4, 2 minus, goes to platinum plus Cl minus. So is the first one. I'm going to balance this guy before I balance the other guy. Step 1, balance all non-oxygen elements. 1 platinum, 1 platinum. 4 chlorides, 1 chloride, so I'm going to put a 4 there. Balance oxygen. There's no oxygen. Balance hydrogen. There's no hydrogen. Balance electrons. So there's -2 on this side, and there's -4 on this side, because there's 4 chlorines. How do I make -2 equal -4? I add 2 electrons. 2 electrons. That's one guy. Now the other guy, aluminum, goes to aluminum 3+. There's 1 aluminum, that's balanced. No oxygens, no hydrogens, so I just add 3 electrons. Now, what's the greatest common factor? 3 and 2 are 6. So this one's going to be a pain in the butt to balance, but it's, so you'd say 2 aluminum plus 3 platinum chloride, or 2 minus, goes to...
Why are you choosing greatest common factor? Like, where are you
because
getting that?
we want the electrons to cancel out. You always want the electrons to cancel out. How do I cancel 3 electrons out with 2 electrons? Well, I'm going to need 6 on the left, 6 on the right. And then 3 times 4 is 12 chlorines. Minus. Okay. Now, if we look at the total charge on the, I'll just do it. The total charge on the top, 3 times 2 is 6. The total charge on the bottom, 2 times 3 is 6 plus, but then 6 plus and 12 minus give you -6. -6, -6. They're all balanced. But so I need to balance each half reaction and then recombine them together. Now, what is the cell potential for this previous reaction? So I'm going to look that up. Look that up on my table. Once again, this is in a textbook that I have here laying over here. But Wikipedia, if you look at standard cell potentials, your online textbook, I'm going to look at what's platinum. Platinum chloride plus 2 electrons goes to platinum plus chloride. After I finish this problem, I'm going to stop the meeting, but we have a minute or two. So the platinum one, the platinum reaction is as written. Platinum chloride, E is equal to 0.73. Now, the aluminum, we have aluminum 3 plus, E is equal to, I'll find what the hell it is. Aluminum 3 plus is -1.66. Okay. You notice this one, platinum chloride. We have platinum chloride on the left, and this one has platinum chloride, would be a reagent. So this one we're using as written. This one, I didn't write the whole equation, but it's aluminum 3 plus goes to aluminum solid. This is opposite of what we see here. This is aluminum solid going to aluminum 3 plus. Because that is opposite, it's going to be the oxidation, not the reduction. So the E cell is going to be the one as written, the reduction minus the oxidation. Now, I could have been mean and made this a negative number, but I chose not to. This is a spontaneous reaction. 7.3 minus a negative 1.66 gives us 2.39. Doesn't matter that there is 2 and 3. No, it does not. It does not for E-cell. E-cell takes that into account. However, Gibbs is not so forgiving. Gibbs, the last one, is delta G equals negative NFE divided by 1,000. To turn this into kilojoules. So F is a constant. E is this number. N is the only thing that can trip you up. How many total electrons are transferred? This is where that greatest common factor came in. 3 electrons there, 2 electrons there. Greatest common factor, GCF, was 6. So N is equal to 6. So we're going to say negative 6 times 96485 times 2.39 divided by 1,000. So negative 6 times 96485, 2.39 divided by 1,000 is still incredibly big. It's still negative 1,383 kilojoules. Negative 1,383 kilojoules to make that reaction go. So, holy cow, that is spontaneous. Most cell potentials with a big cell potential are spontaneous.
Because it's so big, is that why?
Well, it's like, because, yeah, it's essentially, you're transferring a lot of electrons. Well, just these reactions want to go. They want to go due to the nature of this electrical production. What makes these so good? Okay, I'm going to go ahead and stop that. I will rejoin you in a minute. So, stop share, and okay, in order to save time, I'm going to go ahead and skip number 3. Number 3, you can watch the video, you can read the slides, you can do some research on your own. I mean, that's not even necessarily what I'm going to ask again. So, give a real life example of entropy increasing. Pretty straightforward. Find out where randomness is going up. Accuracy, creativity, originality. That might show up again. Might show up again because ideally, hopefully you don't have the same damn thing as everyone else. Although I don't see like forest fire or something like 30 forest fires. That kind of just not very interesting. Okay, let's look at number 5. Oh wait, let's see. Number 5, number 6. Okay, maybe number 9. Okay, let's go right off. Considering the balance, this balance is already balanced chemical reaction. Which molecule compound is being oxidized? Which is being reduced? How many electrons being transferred? So this one you actually have to think. So you got to go. Chlorine is an element. So chlorine is 0. Iodine is an element. Iodine is 0. What is the charge of chlorine here? Which is the charge of iodine there? So the overall charge is -1, and oxygen tends to be -2. -2. So 2 negative times 3 is -6. So -6, oh shit, it's not balanced at all. It's not balanced. No, that's unfortunate. Now it's balanced. Don't ask me why that happened. Okay. So chlorine is going to be negative. Chlorine is negative. I mean, all the oxygens together are -6. The sum of chlorine plus oxygen is equal to -1. So chlorine must be +5. So each chlorine is going from 0 to +5.
You don't look at the coefficients when figuring that up, do you?
No, I do not have to look at the coefficient. When I do this in the presence of, oh, that's why, Jesus. There's a goof in the book when I wrote that. They have chlorine. Yeah, there's a goof in the book. Wow.
Write a letter.
Yeah, no, it's an old book. It's my old book. It's a book but okay, that's why I use things right out of the book, and that's the problem. But you could look this up in the book and find this each half reaction or close enough, and you would see that chlorine is going +5 and iodine is gaining 5 each iodine. But so which molecule compound is being oxidized? Oxidation is the one that is gaining. This goes from 5+ to 0. And this would be opposite of what it appears in the book. Which guy is being reduced? The guy who's gaining electrons. Chlorine goes to chlorate. This is the one that appears the same as in the book. That's each chlorine is gaining 5 electrons. How many total electrons are being transferred? Well, 10. That's a goof in the book. Not balanced, not balanced. Don't ask me why, I don't know. What is the electrochemical cell, though? That part I assume is right in the book. That part.
You repeat which one was reduced and oxidized?
Okay, I'll go ahead and. Oh, the chlorine is this. I'm going to write these from the table. From the table. So, I think I'm wrong. I think it was like so. From the table in the book, ClO3. This is how it appeared in the book. Though, as I said, this was wrong. This has a little goof in the book. Sorry, 6H plus 5 electrons goes to Cl2 and 3 water. So this, and that with the E is equal to 1.47. Okay. Yeah. So this is one of the half cells I used incorrectly because it was typo in the book. Things happen. This is the half cell for iodine that's in the book. 5 electrons plus 3 each. I gotta find where this one appears in the book. Oh, there it is. 1.195. Okay. Oh, man. Okay. So okay, these you can literally look these up in the book, and this is what it gave me. this is what it gave me. Now, what it should have read is this, a half molecule of this. And it won't let me edit. Oh, wonderful. Okay, wonderful. Okay, delete. Okay, oh, God's sake. Oh, there we go. Okay. Select. It's gonna bug me. Okay. Okay, whatever. Okay, so this is what you see in the book, and this is what you see in the book. Which one of these guys appear? Both of these are reduction reactions. Which one of these reduction reactions matches the equation more closely? The reduction reaction that matches the equation more closely is the iodate goes to iodine. Iodate going to iodine is thus the reduction. Now the chlorate to chlorine is opposite. The chlorate to chlorine is opposite from what it appears on the table. So if chlorate is not going to chlorine, but chlorine is going to chlorate, chlorine is being oxidized. So the guy that matches the table is being reduced. The guy that is opposite from the table is being oxidized. And so, and we always use it, the guy that matches 1.195 minus the guy that's opposite. So this is a case that this is a non-spontaneous reaction. You may want to treat this as always positive, but you have to use the equation that is given. You have to use the equation that is given, and this is the equation that is given. Now, using the E cell, what is the equilibrium constant at 25 degrees? My E cell. Now, please note, you will see this a different way in the book. You do not do. I don't like to do this, so I'm gonna always put the numbers in here. RT, N, F, ln, K. Now you may see it as they abbreviate it 0.059 over n. But note, they changed the natural log to a normal log when they do that. That's why I don't like abbreviating RT over F. They changed that. Be careful. If you use that shorthand notation, it changes your natural log to a log, which drastically changes your answer. So I don't like doing that. So negative 2.75 times the moles. Based on the balance equation, I said there's 10 electrons. So times 10 times Faraday's constant, 96485, divided by R, divided by temperature 298. So I get negative 107 equals ln of K. So as I raise that to the inverse log, I get, what is the equilibrium constant for this? 3.08 times 10 to the negative 47. Is that product favored or is that reactant favored? Well, they say, well, that's reactant favored. So is this going to go on its own? No, not really. How will you make it go? You put electricity in it and force it that way. So Answer the following questions about this. What is the Gibbs energy at 25? What would the equilibrium constant K be at 25? And what is M, and if these are constants, what are non-standard Gibbs? Now, because I have specifically given you this at 25, it's not cheating, but I can use the delta G values directly. Because delta G from the table assumes 25 degrees. So let's look these up. Delta G of H plus. Delta G of H plus, I do believe, is 0. I'm going to double check, but I do believe that is 0. We set this guy as 0. So H plus, go back to annotation mode. H plus delta G is 0. O2, because it's a pure gas, is 0. Water. Oxygen. Water. Note, water is in a liquid form. So water in liquid is negative 237.13. 37.13. We want to make sure you're using them in the proper formats. If you use them in a different format, you're going to get a different number, which is why you definitely want to make sure you're using it from the right source. Ugh. Fun. I don't have MnO2 plus. Shit. This book. Okay. MnO2 is MnO2 464.8. Shit. Okay, that's a problem. I have to consult a different book. The book I have does not have Mn2 plus. So that's another reason to make sure you're using a good source, because not all these sources will have all the elements. You might have a shorter source. Okay, let's see. Okay. Okay, that's good enough. Okay. The source I'm using, Mn2 plus. Your numbers may vary a little bit depending on your source. 228.1. Though guaranteed, if I write this test, it'll probably be off data from the online textbook, meaning that you should be able to find all the data in the online textbook with some regularity. But okay, I got all my values. So products to water. So negative 273.13 times 2 plus my Mn2 plus, which is negative 228.1 times 2 minus my reactants. Minus my reactants. Minus MnO2, which is negative 464.8 times 2. Once again, hydrogen and oxygen do not count. So my delta G at 25 is negative 72.86. So the next thing, you're going to use that value for the equilibrium constant. Delta G equals negative RT ln K. So we're going to say, well, delta G divided by 1,000 to get this into the right units. Actually, sorry, times by 1,000. Times by 1,000, because we want to get kilojoules into joules. So negative 72.86 times 1,000 divided by negative 8.314 divided by 298. I get 29.4 equals ln of k. And I inverse log that to get what is my equilibrium constant for this? 5.9 times 10 to the negative 12. Oh, 10 to the positive 12. Sorry. 10 to the positive 12. Spontaneous reaction is product favored. Spontaneous reaction is product favored. So it's 5.9 times 10 to the negative 12. Now the final thing. What is the Gibbs non-standard if at these concentrations? So G equals G naught plus R T ln Q. Q is products over reactants. Products over reactants. So products O2 times Mn2 squared over H plus to the fourth. And how do you find H plus from pH? We take 10 to the negative pH. So H plus of H plus this number, 4.5, is 3.16 times 10 to the negative fifth. That's H plus. So now plugging that in. So our Q value, 0.0082 times 0.0025 squared divided by 3.16 times 10 to the negative fifth to the fourth power. Our Q value, Q is equal to 5.13 times 10 to the 10th. So I'm going to take that number. I'll take the natural log of that number times R, 8.314, times T, 298, and divide by 1,000. Divide by 1,000. So I get positive 61.1 as this whole term. So positive 61.1 plus a negative 72.86. Under those conditions, our G non-standard is equal to negative 11.75 or 76. Under those conditions. So real life, so because delta G assumes 1 molar, that would have been pH negative, what pH of negative log of 1 is pH of 0. So in a very dilute and a moderately acidic pH, even under these low concentrations, we have under these very low concentrations, it's very, very spontaneous. Well, I mean, it's still spontaneous, just not so much. Okay, we're running out of time, so let's go. Let's see. Real life situation where spontaneity occurs. Just thinking here. Explain why the E cell values of iron will typically exist as FeO and Fe3O4 in anaerobic acidic waters, and why O2 is needed to completely oxidize. Basically, if you look at this and you look at this, the cell potential to go to FeO and Fe3O4 is low enough that acid can oxidize it. But going from Fe3O4 to Fe2O3, you need stronger oxidant. And so you need oxygen to fully oxidize iron, to fully create rust. Iron will still degrade in acid, but it won't turn into rust in acid. The final question was looking at this. Okay, answer this question. What is the cell potential of this reaction? What is the Gibbs energy? Looking at sodium portion of the half reaction, how much sodium could be electroplated? And looking at the whole reaction, what is the enthalpy of this reaction? Might this be good or bad, how you look at it? Okay, so breaking this down back into our thing. We have Na solid goes to Na plus. Na solid goes to Na plus. Gotta work fast. I don't have that much time. I probably have enough time to do this. I closed one book to. So Na solid goes to Na plus because you're reading this left to right. Left to right. Na solid goes to Na plus. That has a cell potential. Let's see. I'm going to find it on the table. Damn things are alphabetical. Na solid to Na plus. The I notate. In the book, it says Na positive goes to Na solid is equal to negative 2.71. Hydrogen is 0. So Na solid, so this one is identical as it appears. This one is opposite as it appears. So I'm going to say 0 minus a negative 2.71. This guy is 2.71. Based on that potential, what would be our Gibbs free energy? Well, we're going to, this will actually depend on how many electrons you say are transferred. Based on how this is written, you could say 1 electron or 2 electrons. I'm going to go ahead and say 2 electrons. But E equals what? Delta G is equal to negative NFE divided by 1,000. Is this spontaneous? Oh God, yes. Oh God, yes. So negative 2 times 96485 times 2.71 divided by 1,000. You get the delta G is negative 522.95. I'm going to skip C just to answer D real quick because this is kind of an interesting one. The delta H for hydrogen plus and hydrogen gas are both 0. The delta H for sodium is solid is 0. But the delta H for sodium aqueous is negative 240.1. So the delta H for this whole reaction is negative 240.1, possibly times 2, depending on how you balance this, minus a whole lot of zeros. So what does that mean? It produces a lot of heat. What is a byproduct besides that heat? Anyone? What can anyone see why this might be a problem? What's the problem with too much heat? What is a byproduct of this reaction?
The hydrogen gas?
Yes. Hydrogen gas plus enough heat to auto-ignite.
Well, then you have a combustion. You have an explosion.
Yes. So you throw sodium into water.
To cool it down?
Well, no. You throw sodium in water, it does this. Sodium explodes because if you put this in there, that's the same idea of cesium. We watched the cesium reaction like earlier this semester. You drop a speck of cesium into water, it produces hydrogen gas, and it produces enough heat to auto-ignite when it explodes, destroying the container. So, yay. Okay. The last one. Looking at the sodium portion of this reaction, how much sodium can be electroplated back onto the electrode running a current of 50 amps, run for 30 minutes. So 30 minutes, how many seconds is that? 30 times 60. Time is 1800. Let's say we want to get one electron. So the thing is, we want a mass. What is the mass if we have current time times molar weight over NF? So it doesn't matter what voltage it is. It only counts for time, current, and what we're electroplating. So 50 amps for 1800 seconds times the molecular weight of 23 grams per mole divided by 1 electron divided by 96485. You could deposit 21.45 grams. 21.45 grams in that period of time. Okay. Oh, jeez. Okay. So that is all the relevant questions of math on this. That's all of the math questions on this old test. I think I posted the worked out version of this online already, but I wanted to work this out fresh with you. I wish I had a little bit more time, but look for something like this. This is a pretty good scope of things. We have in here turning E and delta G into K. We have here calculating delta G at various situations, calculating E in various situations, occasional balancing these guys, understanding what it means to be an oxidation and reduction, looking at these. So this is what these two chapters are. So measuring this, there might be something like predicting entropy or something like that, or understanding entropy. So, but this is a good feel for what the test is going to be similar to. As I said, when I get the test done, I will send it to you. It'll probably be due on Friday. Not sure if I'm doing a final or not. Test 4 may be the final, or I might just like make all the tests worth more. I don't know. The final might be just for worth less points. Or I have no clue what I'm going to do because I can't exactly give you the standardized final online. And I can't exactly bring you all in from wherever the hell you are to take this final. So we will see what I decide to do. But let's, in the meantime, get all the homework in, get all these, get this test done, and we'll work from where we're at. It just be this, as I said, the lost semester for our like measurements, for like our standardization. But as I said, go ahead and cite where you got your values. You may want to be consistent because the values will change. Sometimes the values change greatly, but sometimes it's just a tweedling effect. Like it changes by like a couple kilojoules one way or the other. But use it. Said, I hope more people are using the videos, but yeah, I'm getting a couple views here and there. Like, subscribe, yada yada yada. Monday, I'll just be doing nuclear chemistry just for shits and giggles. You guys don't have to participate.
Thank you.
I don't think I'll have to do organic. I mean, I don't think I'll have to do homework for that.
If we
but-
do homework, is it extra?
But I mean, I can give the homework as extra points, but I'm not sure it's extra credit. But I was gonna say, like, I'll probably still do clicker. So if you hang around, you can still do clicker from some free extra points, no matter what. But yeah, we'll do. If you're not there, you're not there. It's not a big deal. One of the things we'll look at is like it'll circle back to kinetics again, but not too much because it's all first order. Okay, that's all I got for today. We're already over time. They want to kick me out, so hey, this video hopefully will be of some help as you're working through the test. But so it's already, I think, worked out in all in Schoology.